So thank you so much to the organizers for the opportunity to give this talk. As I mentioned yesterday, I'm Fraser. I'm a PhD student at Harvard University, and I'm talking today about Axion mass from magnetic monopole loops. It's based on this PRL put out with my advisor, Matt Reese, as well as my collaborators, Gigi Fan and John Stout. So I want to start by giving a little bit of motivation. So the motivation for thinking about this is really the types of searches that we do for axions. So as we all talked about yesterday, and as people in this room are familiar with, the easiest coupling to look for axions is often the axion photon coupling. In contrast, when we're talking about solving a strong CP problem, what we're interested in is usually the axion gluon coupling. And so in the standard UV completions, we get some sort of target right here for the KS, PZ, and DFS UV completions. But experiments are kind of probing the rest of this parameter space. And some of that parameter space is model dependent. But we can ask the question, can we say anything about the axion? Can we say anything about the axion properties when we don't have a gluon coupling? And so the typical story of how the axion gets its mass is that the QCD axion gets a potential that can be computed with instantons at high temperature, or if at low temperature, it can be computed using the Carl-Lagrangian. But none of these types of effects exist for abelian gauge fields. And so we run into the question of whether or not these axions can be massless. And if not, what is their mass? And we can get some answers from quantum gravity. So quantum gravity tells us that axions should not be massless. And the reasoning behind this is this no global symmetries argument from quantum gravity, because massless axions would have a continuous shift symmetry. So the way this no global symmetries argument works, it can be derived fairly generally from black hole arguments. So if you imagine taking a black hole and throwing in something with global charge, say B minus L charge, like a neutron, you can throw any number of neutrons you want into that black hole. And because of that, you can give that black hole any charge that you want. Now you can imagine waiting for that black hole to evaporate down to some size lambda quantum gravity inverse, but it won't shed any of that global charge. And so because we can do this for any charge, we can create black holes of any charge of this size. But that's problematic in the language of quantum gravity because we expect that in a finite region of phase space, finite region of space-time, we should only have finite entropy, which corresponds to finitely many states. And so we can't have these continuous global symmetries because we'd have an infinite number of black holes, which is an infinite number of states. The difference between this and gauge charge is that you can, with the electric field, you can emit gauge charge. And so this same argument does not apply to the case of gauge charge. So quantum gravity tells us these axions should not be massless, but it also rescues us because it gives us something else, which is this completeness hypothesis, because it tells us that the completeness hypothesis says that monopole states should exist because they're necessary to break one of these global symmetries. So the combination of those two things allows us to get a new contribution to the axion potential that comes from loops of magnetic monopoles. Yes. The argument, I think, is more complicated in the case of discrete symmetries. There are certain types of discrete symmetries that I think are allowed. I think so, but I'm not as familiar with the case of discrete symmetries, and it's not necessary for this argument. Yeah. Yeah, and actually this effect ends up being exponentially small because it's the effect that we find is exponentially suppressed because it's from a soliton. So the fact that it's exponentially small actually is not a problem for us. We just don't expect it to be a perfect symmetry. Okay, great. So we have from quantum gravity that we expect monopoles to exist. I don't mean a cosmological abundance of monopoles, so we don't necessarily have to have some plasma of monopoles, just that these states exist in your theory. And from that, we can get a new contribution to the axion potential. So there's 3 steps to this argument. First, in the presence of a theta angle, monopoles acquire electric charge and become dions. This is the Witten effect, which was derived in the 1980s. Second, because the electric charge the electric charge changes the dion mass in a theta-dependent way. And third, axions get a potential when we integrate out the dions. So these first two effects just depend on the fact that we have a theta angle. And then this is where we actually are talking about a dynamical axion. Okay, so this is the general kind of overview of how it works. So let's get into details. So first, the Witten effect. So the Witten effect tells us that monopoles in the presence of a non-zero theta acquire electric charge. And the nicest, most physical argument for this, though it's certainly not the only one, is this argument by Wilczek, which says, imagine you have a region of spacetime that has theta equals 0, surrounded by a region of spacetime with theta not equal to 0. And put a monopole inside the region where theta equals 0. Then, if you look at just the equations of motion for this system, you'll see that as you change theta across this boundary, in the presence of a B field, you expect an E field. And if you integrate both sides of this, what you find is that the electric charge does not depend on the radius. And so you can take the limit as the radius goes to 0 because the electric charge is independent of the size of the inner region. And so you still expect this to exist even the small radius limit. And I guess I should comment that technically you really just need to take this to the radius of the monopole. You don't necessarily need this to be 0 if you're not talking about a point monopole. It's good enough to take it to the monopole radius. So this tells us that this type of argument tells us that monopoles in the presence of a non-zero theta acquire electric charge. That's step 1. Yes. This is from 87. Good to know. I will include your citation as well. So step 2, the electric charge changes the dion masses in a theta-dependent way. So this is a very general statement, but it's easiest to see through an example. So I'm going to go through an example for it. So the simplest example that people often use for the case of monopoles is the 't Hooft-Polyakov monopole, which shows up in the Georgi-Glashow model. So for those who are unfamiliar, the Georgi-Glashow model has this field content here. It contains an SU2 gauge field and a scalar triplet field, and then there's a potential for the scalar. And if we compute the, we find in this model that there are topologically non-trivial configurations that look like monopoles. And if we compute the energy, we can find by minimizing this energy. So if we compute the energy, we get this expression here. And this term vanishes along the equations of motion. And this turns out to be equal to the mass. So this turns out to be equal to the mass, which is just V times the charge. So that's the classical Georgi-Glashow model. If we want to see this effect, we need to quantize. So how do we quantize a soliton? We quantize a soliton by studying its collective coordinates. So the collective coordinates parameterize the symmetries that are preserved by the Lagrangian, but broken by the actual state. And so in this case, there's 4 collective coordinates. There are 3 translations. You can move the monopole anywhere you want. And there's also an unbroken U1 in the Georgi-Glashow model. We broke an SU2 down to a U1. And so there's a coordinate sigma that's periodic that parameterizes that unbroken U1. And if you look at the variation of these collective coordinates with time, you can derive an action from them. And you can quantize that action. And what you find is that the energy is proportional to Q squared over the radius of the monopole, where Q is dependent on theta. And you can see there's this linear dependence here, where here on the y-axis, I have Q, and here on the x-axis, I have the value of theta. And so you see in the 't Hooft-Polyakov case, you find a theta-dependent energy or mass. And this effect appears more generally. You can see this by looking at various corrections to this. But the details of the corrections aren't particularly important. So step 3, how do we get from there to the axion potential? So we're going to compute the effective potential using the word line formalism. So in the word line formalism, the effective potential is given by 1 over the volume times the log of the path integral. This just comes from the fact that the path integral is e to the minus s. And in particular, when we're doing this path integral, we're summing over all of the paths the monopole can take, so all of the monopole word lines, and they should be periodic because we want an effect that's just the mass that's just there, so we want it to start and end in the same place. And for the case of weakly interacting, so that tells us we're dealing with things that are topologically a loop. For the case of weakly interacting monopoles, we expect each of these to have its own distinct disconnected path. We don't take into account interactions of these different paths. And so because of that, what we end up with is that this z theta is just a sum over whatever we get for one path exponentiated up to some combinatoric factor, 1 over n factorial. And so if we plug this in, we find the effective potential is just given by minus this limit of 1 over the volume times this transition amplitude for the circle. So the transition amplitude for trajectories that start and end at the same point. And so we need to actually compute that transition amplitude. And the easiest way to do that is to integrate out this tower of heavy dyons. So the Witten effect told us that when we have a magnetic monopole, we're going to get this tower of particles that also have electric charge. And so we can use the background field method, treating the axion as background field to get to integrate out that tower. So in the world line picture, the free particle propagator is generally given by this expression here. So here, this propagator depends on the starting and ending position. It depends on the mass squared. It depends on tau, which is the invariant length or Schwinger proper time for your path. So that's the size of your circle. And what we're doing is we're doing a sum over all those different circular paths. So here, ZFS1 is that sum. You take this expression here, plug in x prime is equal to x, so this term goes away. For the mass here, you want to plug in the dion mass. We want to, which is proportional to the monopole mass plus some spacing, m delta squared times n minus theta over 2 pi squared. So this is a theta dependence. We want to integrate over the different path lengths. So that's integrating over tau. We also get this extra factor 1 over 2 tau here, which comes from the fact that these are circles. So you can flip them or you can rotate them. And we need to get rid of those degeneracies. And then we're summing over all the different states in the tower. So we do this sum and we plug into the expression for V effective on the previous page. We can also rewrite this. So right now we're summing over the states in the dion tower. This expression is pretty small, but this is just an expression for the to do Poisson resummation. So we're just switching the states in the dion tower. Instead of summing over n, we want to sum over the number of times we wind around this collective coordinate L. And so after doing some mathematical manipulation, what we find is that for a general monopole, we expect an expression of this form. So we expect an expression that goes like E, as I was saying at the beginning, it's exponentially suppressed, e to the minus ls. Here, this s is 2 pi times the monopole mass over m delta. So that's the monopole mass over the spacing. And something that's really interesting that shows up here is that if you plug in the 't Hooft-Polyakov case, what you find is that this action looks like 8 pi squared over g squared. And that should look familiar because that's the exact same expression we get in the instanton case. And so this is a very interesting hint that perhaps this could be connected in some way to that, though we are conjecturing that. We don't have a way to prove that yet. Yes. So it doesn't have to be. That's the example we talk about, but this effect is general. So this form of the potential is general. This relies on the fact that you have 't Hooft-Polyakov, so that specific form. Yeah, that's what we conjecture. We don't have a way to prove that they're exactly the same, but we suspect that this is a low energy description of that same thing. But let's say you have a string theory UV completion and you don't necessarily know how to do the calculation in some non-abelian theory, for example. This is another way to get that answer using only UV physics. But yes, we expect it to be connected, though we can't prove it yet. Yes. We don't assume the presence of the dianic coordinate. It falls out of the derivation. So if you so monopole, that's true. Things like the Kaluza-Klein monopole don't have a diagonal collective coordinate, but they also don't have an axion coupling that falls out. So the monopoles that have an axion coupling of the form theta f wedge f also have a diagonal collective coordinate. And we suspect, we're working right now on thinking about how this relates to the presence of fermions and more complicated things. But you expect that in all the cases that we know of that have an axion, you have a diant collective coordinate. If you don't have the standard axion coupling, then you don't necessarily have a diant collective coordinate. I think so, yes. Maybe we should talk about that more at the coffee break then. Other questions? Yes. Sorry, the what to infinity? Sure. Yeah, you're neglecting the radial mode. That's true. I don't think the radial mode affects any of this because you don't get the same type of coupling for the radial mode. There's probably a small like subdominant shift I would expect, just the same way like whenever you have a pseudo goldstone, right, that you can get a tiny shift in the VEV from you know a potential along the theta direction, but it's so subdominant that I mean if it's exponentially suppressed compared to the VEV, it wouldn't be relevant. I think it's just the G of whatever you have at your low energy scale. So this only talks about the broken phase. So whatever G is relevant in your broken phase should be the one that shows up here. Other questions? Okay. So I also want to comment that there is another way to see that you get this effect. To do this last step here, this integral to compute this potential. And that's to directly do a sum over winding around this collective coordinate. So we started by integrating out this tower of dions. Instead, if we wanted, we could treat that collective coordinate as an extra spatial direction, as a compact spatial direction, and compute the same type of calculation for that expression. So the action here would look the same as before, except we also have an extra term from this compact spatial dimension. Now our free particle propagator needs to sum over the windings from x to x prime, but also, it's a typo, that should be x prime. And also theta goes to theta plus 2 pi L. And the rest of the propagator has a similar form to before. And so now we'd want to sum over the connected paths again. And if we do the same type of calculation, what we end up finding is the exact same answer. So whether or not we compute this by integrating out a tower of heavy states and then Poisson resumming, or summing over the connected paths, we end up with the same thing. Okay, so to recap how we get this effect, there are 4 steps. So we expect these monopole states to exist. This was from quantum gravity. This didn't rely on a plasma of monopoles, just relied on the fact that there are states in the spectrum of your theory. Then in the presence of a theta angle, monopoles acquire electric charge and become dions. This is the Witten effect. Then the electric charge changes the dion masses in a theta dependent way. And from that, we can integrate out these heavy tower of dions and get that the axions get a potential when we integrate them out or when we sum over winding. So this is the big picture of how this effect works. Now, what can you do with this? So in order to explain what we can do with this, I want to draw a distinction from previous work. So previously, Fischler and Preskill, as well as several more recent papers, have found an effect from the axion potential that comes from monopoles but theirs is actually from a physical monopole anti-monopole plasma. So they find a thermal contribution to the potential that's generated by monopoles and anti-monopoles. And that depends on things like what type of phase transition you have, what the actual plasma is, et cetera. That's distinct from our contribution, which is only talking about these virtual monopole and dione states. And if we want to look at a phenomenological example, the simplest thing we can do is we can talk about a dark U1 sector. So we consider a model with a hidden gauged U1 dark and a spontaneously broken U1 Pesci-Quinn. Then the total mass of the axion is going to be a contribution to this from this thermal plasma that was previously known, a sum of that with the loop contribution. And what we find is that in some regions of parameter space, our contribution is dominant. So on this plot here, I have monopole mass versus the coupling. Now, below this blue line, there would be no axion oscillations today, so the axion couldn't be dark matter. Above this green line, the combination of axions and monopoles would be enough to overclose the universe, so that's forbidden. And then these dotted lines, which are also a little hard to see, are the fraction of dark matter that's the axion. So this is 10 to the minus 3, 10 to the 0.1, and 0.99. So you can see this changes very rapidly. And so this region between these two is the allowed region. And you can see for quite a substantial fraction of this, this is the dominant contribution to the axion mass. And so this becomes very relevant when you're talking about early universe scenarios. So in summary, the axion's compact field space constrains its coupling to topological defects and can give qualitatively new effects. So that's the reason we see interesting effects like this for the axion and not for other particles. And here we specifically show that this is what leads to a new contribution to the axion potential when the axion is coupled to abelian gauge fields. And it comes from heavy dions and is generated by the Witten effect. So next steps, things that we're currently thinking about are, one, what happens when you add light fermions? So as we all know, the massless up quark solution to the strong CP problem says that if you had a massless quark, the theta angle would become unphysical. We expect this effect because we get a similar rotation. If we had a massless quark, we would expect this effect to go away in the massless limit. But it's challenging to understand the behavior as we go toward that limit. And so this is tied in with things like the Kalin-Rubikov effect, potentially. And so we're thinking about trying to understand that right now, but we don't have a solution yet. Second thing is the potential actually dominated by single monopole loops? So we made the assumption that you could sum over disconnected loops, this exponential, but maybe there are some long-range Coulomb interactions that you would need to take into effect. We think that this should be the dominant contribution because you have weak coupling. This is the same approximation you're making in the instanton case in the form of the dilute instanton gas approximation. But potentially you could look at corrections to that. So that's one thing we are also interested in understanding. And then finally, we can ask what was asked before, which is, can you formally connect this to the instanton potential in the UV? And with that done, and this idea here that the axion's compact field space is what gives us these interesting new effects, I want to give a very brief preview to some ongoing work, which is only going to be a couple slides. So as those of you who were here last week probably heard about axion strings. And another example of where you can get these interesting effects is axion strings. So it's well known that in the background of an axion string, bosons and fermions can have trapped massless modes on that string and can lead to superconductivity, which is a current that grows with imposed electric current. This was first stated by Witten and also shown using some more formal arguments by Kalin and Harvey, anomaly inflow, as well as this recent paper also explores this. And so we can show explicitly that these massless modes exist, but there's a common and intuitive explanation, which is that we expect modes to be massless because as we go toward the string, the potential goes to the potential goes to 0, and so we expect something massless to show up at the core of the string. And so our work is looking at the fact this actually isn't necessary by studying a massive Dirac fermion. And we find that you can get 0 modes. Even when you have bulk particles that are massive everywhere, there are still separate modes that are localized to the string. which has interesting potential phenomenological consequences for DFSC axions because you see something similar there, which is something that we're still working on. So this work should be out hopefully next month. Some of you, if you've been here a while, may have talked to Hengama about this earlier in the month. But I just want to advertise that this is an exciting next step, another exciting application of the interaction of axions and topological defects. And I'm happy to chat more about this, either answer questions or over coffee. Thank you. Yes. So this argument. Yeah, so the idea is that this previous potential was thermal and it was based on thermal QFT. And so the important thing isn't so much that you have anti-monopoles, it's just that you have a gas of those monopoles. You have a physical presence because if you don't have some physical, interacting plasma of them, you don't have any temperature. And so it's that temperature dependent effect that requires that you have a physical plasma of them. So right now, this is about a dark hidden U1. So this definitely affects, which it affects very low masses. So it prevents you from having a mass below a certain amount. That depends a little bit on the model, but it prevents you from having very, very tiny masses. We're hoping that in the case of an axion-like particle that interacts with the standard model U1, you should be able to get a similar effect, but we need to understand fermions because the light fermions interact with the U1. So once we understand the light fermions, then we should be able to see a similar effect for axion-like particles that interact with the standard model U1, but we're not quite there yet.